Hello, this is Farhan Shakil from the Republic 2.0, and in the last part of this video, we have almost covered the first 16 questions of this paper. This paper is from May 2025 of Unit 1, International Edexcel Physics. So we'll start from the part where we left out the last time, and we've got this question number 16 right over here. Here we go. So we've got this question now, and a student used a falling ball method to determine the viscosity of the vegetable oil. He measured the diameter of a ball bearing. He dropped the ball bearing into a measuring cylinder containing the vegetable oil, blah, blah, blah. The ball bearing reached the terminal velocity. The student then measured the time taken and the ball bearing. So you've got the time, you've got the distance, and you've got the diameter as well. Now you need to determine the viscosity, right? If you all remember, the formula for the viscosity, whatever we're going to use, is going to be the drag force equals to 6 pi eta RVT. So if you look into this formula can also be written as the drag force, which should be equal to the weight displaced of the liquid, 6 pi eta RVT. So from this formula, you can calculate the terminal velocity if you've got the time and the distance. You can calculate the radius from the diameter given above. The only thing that you do not have, G and pi are the constants. So the only thing that you need to measure is the mass of the ball bearing. So the only thing that we need to measure is the mass of ball bearing. That is what we need to look for. Now in the B part of this question, you need to calculate the diameter of the ball bearing. And it was 1.24 millimeters. So what does that mean? That the radius has to be 0.62 times 10 raised to the power of -3 meters. The time taken to fall is 20 centimeter was 1.3 seconds. What does that mean? That the terminal velocity has to be 0.2 divided by 1.3, whatever it comes out to be. And then at the end of the day, we've got the drag, and that comes out to be 5.6 times 10 raised to the power of -5 Newton. So by using the same formula that the drag force is equals to 6 pi eta RVT, we can calculate the eta, and the formula for the eta is going to be FD divided by 6 pi R times VT. Is that clear? And now we just need to plug in the values. You've got the FD that comes out to be 6 pi eta RVT. Oh, you've got the drag force already. And that drag force is, or the viscous drag is 5.6 times 10 raised to the power of -5 divided by 6 times 3.14 times the radius is going to be 0.62 times 10 raised to the power of 3 and 10 times the velocity. The velocity has to be 0.2 divided by 1.3. So you just need to divide them up. And by dividing them up, you'll get some viscosity that should be 0.0311 pascals second. So that is how you'll be looking for the viscosity. And now you've got the C part, right? The student repeated the experiment. He used the same oil at a lower temperature. So lower temperature, what does that mean? The liquid should be having a high viscosity. Explain how using oil at a lower temperature affected the time taken for the ball bearing to fall 20 centimeters. So everybody knows that whenever you're talking about lower temperatures, right? At lower temperatures, you must be having a higher viscosity, right? 3-mark question, so I'll make sure to write down at least 3 points. Higher viscosity means that the body should have a very small value of terminal velocity. The body should have a very small value of the terminal velocity. And thirdly, if you've got a very small value of terminal velocity, the ball bearing would take more time, right, to fall down, because it is having a very small value of VT, right? So ball bearing would take more time to fall. So that is how we need to talk about all these things. Next, we've got this question number 7. A violin is a musical instrument that has 4 strings as shown. A force extension graph for a sample one of the strings is shown below. You've got this force extension graph. And then, you've got the table that shows the stiffness of the strings X, Y, and Z. We need to deduce that which string was used to obtain the force extension graph. So what does that mean? That we just need to calculate the value of K from the graph. You can all see that, you've got the force and the extension, and there is a Hooke's law that states F is equals to delta F is equals to K delta X. So if you want to calculate the stiffness of the spring, that has to be delta F divided by delta X. The change in the forces is from 0 to 80. That has to be 80 newtons. And the extension, it went from 0 to 30 millimeters, right? This is 30. So 30 millimeters, not 30 exactly, that has to be something like 29, right? So 29 times 10 raised to the power of -3. By dividing them up, you'll get the value of K. And by dividing them up, you'll get the value of K. And that comes out to be something like 2760 newtons per meter. So if you've got this value of spring constant, what does that mean? That the spring that you must have been using should have been Y, because that is the closest value that we can have, right? So we have got the spring constant or the stiffness, and that was 2760. So it was spring Y. It was spring Y. That is how we're going to talk about it. Now, in the B part, the fourth string on the violin has the original length. This is L, right? When the tension applied on the spring is 36 newtons, this is the force, right? The new length of the string, this is the new length, right? So by just taking them away from each other, you need to get yourself delta L, and whatever it comes out to be, that has to be the final answer. If you have got the radius, you can also calculate the area. And now you need to calculate the Young's modulus. And how would you calculate the Young's modulus? Young's modulus is the stress upon strain, right? So the formula would eventually become F times L divided by A times delta L. I'm just going to plug in the different values. I've got the load, and that is 36. I've got the original length, and that is 0.750. I can calculate the area by using pi r square. So 3.14 times 0.85 times 10 raised to the power of -3 square. And I can calculate the change in length by taking 0.750 away from 0.752. And after just solving all these things down, you've got the force, you've got the original length, you've got the area, and you've got the extension. After calculating all these things, you'll be able to determine the Young's modulus of this system. And that comes out to be, whenever you're talking about Young's modulus, the value of this Young modulus has to be 5.96 times 10 raised to the power of 9 pascals. So that is how we're going to calculate this Young's modulus, right? Now we have got this question number 18, where we have got a set of these different spheres which are going to strike along each other. Each sphere has a radius of 7 times 10 raised to the power of -3 cube. Calculate the mass of one sphere. Density of the steel is given as well. So since the density is mass upon volume, so the mass has to be the density times the volume, right? So you've got the density, and that is 7.8 times 10 raised to the power of 3. And the volume of the sphere, that has to be 4 by 3 pi r cube, because you've got the radius and you need to calculate the volume of that sphere. So that has to be 4 by 3 pi r cube. So 4 by 3 times 3.14 times r cube. R has to be 7 times 10 raised to the power of -3 ka cube. You can just simply work this thing down, times them up together, and you'll get the final value of mass. That has to be something like 1.12 times 10 raised to the power of -2 kilograms. That is how you're going to calculate the value of mass. Got it? Now, after this question, we have got something like student pulls the sphere A so that the string is at an angle of 38. So you've got an angle of 38 over here. I'm just going to complete the triangle. The direction of the acceleration would be, since it has got to its maximum position, the direction of acceleration has to be from here, right? So as shown, releases from sphere A. Determine the initial acceleration of the sphere A when released. So you just need to calculate the initial acceleration of the sphere when it is released. So what does that mean? It has to be a vertical component of the gravitational acceleration. So A initial acceleration of the sphere has to be, because we are looking for this component. This is the opposite side of 38, right? So you just need to use sine theta. So you've got 9.81 times sine 38. You just need to work this thing down. So 9.81 times sine 38 would be something like 6.04 meters per second square. That has to be this type of an acceleration, right? So now we have got this diagram number C. Well, we've got all these diagrams. Diagram 1 shows the position of the sphere when the sphere A is released. After being released, blah, 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 they all collide. BCD remains at rest. E moves away from the sphere D. Diagram 2, blah, 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 describes the changes in energy and momentum of the sphere A and E from the time sphere A is released until sphere E reaches its highest point. Ignore the effects of the air resistance. So we just need to ignore the effects of the air resistance. I'm just going to talk about it. This is a 6-marker question. First of all, I'm going to start with this point. A being at the highest mean position. When A was being at its highest mean, at its highest extreme, what does that mean? That initially A had maximum gravitational potential energy, right? Secondly, as it moves as it moves towards B, kinetic energy kept on increasing. Its kinetic energy kept on increasing, right? A had maximum momentum. It would be having a maximum momentum as soon as it is going to strike B, right? So, it would be having a maximum momentum as soon as it is going to strike the P. So now, kinetic energy of A should be transferred to E via the middle balls, right? Via B, C, and D, I guess. Okay. And now you need to you write down two very important lines that since energy is being conserved, right? So energy input of A at B should be equal to energy output of E, right? Whatever energy you have transferred from A here, that must be the same energy when D gonna, make the E pop away. And at the same time, initial momentum, or you can just simply say the final momentum upon collision of A should be equal to the initial momentum of E as well. Well, remember that we're talking about the law of conservation and law of momentum, and both of them should be conserved. So you just need to write down these important points, and then at the end of the day, you need to talk about the relationship between the energy conservation and the momentum conservation of both these bodies. After this thing, we've got this question number 19. A student stores a bicycle on a rack. The bicycle rests on the rail that can rotate about a pivot to take the bicycle off the track, blah, blah, blah. They keep on talking about nothing. When the rail is in equilibrium, the principle of moment applies. What is meant by the principle of moment? Well, everybody knows that. For a body to be having summation torque is equal to 0, the clockwise moment, the total clockwise moment acting on the body must be equal to the anti-clockwise or counterclockwise moment, right? So that is how you need to be talking about these things, right? This is the principle of moment. Now we've got the B part of the same question. We've got the bicycle off the track. The student lifts the rail back to its original position. We've got the original length of the track to be 1.40 and the weight of 95 Newton. So basically, we just need to calculate the minimum value of F needed to lift the rail off the ground. So if you need this force, we certainly need to apply the principle of moment. And whenever you're doing a question regarding the principle of moment, you need to identify the number of forces acting on that whole thingy. So you've got this 160 Newton, you've got this 95 Newton as the weight, and you've got this force. So we have got three forces. So first of all, we're going to calculate the moment due to these three forces. So the moment due to, for example, whenever you're talking about this 160, so the moment of piston about the pivot is going to be, I'm just going to calculate the moment. The force is 160, and the distance from the pivot of this force is 0.37. We're looking for this distance, right? So we've got 18 degrees over here. I'm going to take the vertical component of it, and that is going to be sine 18. When you're going to times them up, you should be having 18.3 Newton meters. So this is the torque due to the pivot. And now you have got the moment of the weight. So I just need to calculate the moment of the weight. And the moment of the weight is going to be 95 Newton, which is the force or the weight of the rod, times, it must be acting at the center of gravity. Since the total length is 1.4, so the center of gravity should be at 0.70 from the one end. And then you need to times it by the angle through which it is subtended by the horizontal. And that is going to be cos 42. When you're going to times them up, you should be having something like 49.4 Newton meters. That is the torque due to the weight. At the end of the day, you've got the torque due to this force as well. This must be F times 1.4. So this F and that 18.3 Newton. Both of these moments are acting in a clockwise direction, and this one is going to be an anti-clockwise moment. So sum of these two moments should be equal to the other one. So 18.3 plus F times 1.4, it should be equal to the moment due to the weight, and that is 49.4. So I'm just going to work this thing down, and force must be equal to 49.4 minus 18.3 divided by 1.4. When you're going to take them away from each other, you're going to divide them by 1.4, and you'll end up having 22.2 Newton. So that is how you can calculate the force required to lift that rail up. Now you've got this second question, and in the second question, you've got the student could have lifted the rail by applying a vertical upward force to the handle. The force needed to lift the rail is different when the force is vertical compared with when the force is, well, for example, if you're applying a vertical force, if you're going to apply the force vertically, the moment of the force should be less. And if the moment should be is less, the force needed should be greater, right? The force needed should be greater. So for example, if you're applying the vertical force, what does that mean? That you need a higher or a greater moment, right? Greater moment, because the moment arm should reduce, right? If you need a higher moment, what does that mean? That, uh, you know, if there is a higher moment, what does that mean? That the force required to lift that thingy up is greater as well, right? So that is why the forces applied along the perpendicular or along the vertical has to be different because the moment arm changes. Now you've got this question number 20, and you've got the time, you've got the distance, and you just need to calculate the mean acceleration is 0.95 g. We just need to deduce that air resistance acting on the Skydiver was negligible during the first 1.5 second, right? Air resistance is negligible if acceleration is greater than 0.95 g. So we just need to work out the acceleration. So I'm just going to use S is equals to ut plus half at square, right? S, everybody knows that S comes out to be 11. Initial velocity should have been 0, so 0 times t has to be 0. 1 by 2, I'm calculating the acceleration, and time is 1.5 squared. So by working out acceleration from here, it comes out to be 11 times 2 divided by 1.5 ka square, right? So I've got something like 11 times 2 divided by 1.5 square. And when you're going to sort this thing down, it comes out to be 9.78. And if you want to write this 9.78 in terms of g, just divide it by 9.81, and that comes out to be something like 0.997. So 0.997 g. So it is preferably 0.997 is greater than 0.95 G. Since if it is greater than 0.95 G, what does that mean? That air resistance can be considered negligible. So they're right in their assumption. Now, if you have got this VT graph, for example, you've got a displacement time graph for a skydiver between jumping from the aerospace and opening his parachute. And you can see that the displacement is decreasing in the negative direction. So the velocity initially, you can see that the displacement was a curvaceous. So, the velocity would increase, but it should be in the opposite direction. And then as soon as the line becomes straight from 10 to something like 22 seconds, you know, it would be something like this, and then it would be a straight line, right? So that is how the graph of the vertical velocity should look like. In the BC part, you have got that after jumping from the aeroplane, the skydiver accelerated. And when the skydiver accelerated, then reached a terminal velocity before opening his parachute. Explain how energy conservation applies to the skydiver before opening the parachute. So when he is jumping downwards, what does that mean? First of all, the gravitational energy must be decreasing, right? The gravitational energy must be decreasing. And when the gravitational energy is decreasing, what does that mean? That the kinetic energy must be increasing, right? Because we need to conserve the energy, right? And if the kinetic energy is increasing, where the other type of energy is going, you need to do the work done. You need to do some work against the air resistance as well, right? You need to do some work done against the air resistance as well. Energy must be dissipated in this form, right? Now, as the terminal velocity is achieved, gravitational potential energy would be all gone, and you would be doing just work done against the air resistance, right? So at the terminal velocity, the gravitational potential energy has to be zero, and all the energy, I'm talking about the gravitational potential energy, it must be dissipated to do work done against gravity, right? That is what we all need to know about. Got it? Now, we've got something like D part. The skydiver opened his parachute and his speed changed. After a time, he reached a terminal velocity. Explain how the forces acting on the skydiver caused this acceleration. How this caused this acceleration to vary after the parachute opened. So first of all, remember that as soon as the parachute gonna open, you all know that air resistance should be bigger than the weight, right? Air resistance should be bigger than the weight. So what does that mean? That the resultant force is acting upwards, right? Initially, resultant force is acting upwards. And similarly, the acceleration of the body must be upwards as well, right? And when the resultant force is upward, the skydiver would start decelerating, right? Acceleration is upward, but skydiver should start decelerating. It would be some sort of a stationary thing up in the air. And after this thing, as the speed gonna increase, after this step, the speed gonna increase. At the same time, the air resistance would decrease as well. And as the air resistance decreases, what does that mean? That now the air resistance plus the upthrust acting on the body should be equal to its weight. And as soon as the upthrust and air resistance becomes equal to the weight, what does that mean? That now the resultant force should be zero and acceleration is supposed to be zero as well. So that is how the acceleration varies from him jumping down the thingy to parachute opening. This is a step when he opens up the parachute, and when there is some time, then this thing is going to happen. So that is how we're going to do this paper. I hope you've got every question of it. If you've still got any questions, you can comment, and I'll try to answer. Thank you very much.